Well, good morning. I'm going to be talking to you about how to package mmWave MMICs. My subtitle here really says what I'm planning to do. I'm going to try and describe some of the technologies, the issues, how to avoid the problems with putting things into packages at mmWave frequencies, and how to optimize the performance. So, the demand for broadband wireless data is what's led to the increased adoption of mmWave frequencies. In particular, the growth in high volume consumer applications, such as 5G cellular and broadband satellite. And with the high volume comes a demand for low cost. Now, if you look at a mmWave SMT packaged IC, it looks very similar to lower RF frequency SMT packaged parts. However, the parasitic effects can be much more significant and the consequences can be very serious. And you have to be extremely careful to avoid degrading the performance. So what I'm going to do is discuss the different packaging technologies, look at the problems of the packaging parasitics, and I'm going to describe some approaches for mitigating them and for implementing high performance SMT packaged mmWave ICs. And I'm going to illustrate this with a number of practical design examples. So this is a summary of the packaging technologies we're going to look at. Now, this frequency range here, this is a sort of guideline. Don't take this as hard and fast. You can never go beyond 40 gigahertz. But this is roughly where you're going to operate to. So overmolded plastic, this is probably the most common form of microwave package for ICs. The QFN style being most common, and it's the lowest cost. And you can get parts operating up to about 40 gigahertz. If you go into an air cavity, this can push things a little higher, 45 gigahertz or so. I mentioned custom lead frames, and there'll be more detail about these later, but these can offer you some benefits in optimizing performance. Laminate packages, this uses the same sort of laminate PCB material that you might use in a PCB, but it uses it to design a package, and this can offer you a flexible means of designing a custom package to operate to 45 gigahertz or so. And you can also buy standard product laminate packages that you can put your ICs into. We've got flip chip, wafer level, chip scale packaging. Now this is a very interesting technology. You can push IC performance up to 100 gigahertz. This is really an addition to the IC fabrication. You add some extra process steps at the end, and I'll describe this, and I've got some images. Multi-chip modules, here we take a number of bare die and put them in a module. There are various approaches, and you can push the frequencies to beyond 100 gigahertz. And antenna in package technology. This can end up with a very compact solution. It is very application specific. You don't end up with single building block components. You have essentially the entire front end in a single package. And we've got an example of that as well. So this is a 28 gigahertz FEM single chip IC in a plastic package. There's a 3-stage power amplifier here. There's a TR switch at the output. There's a little coupler here with temperature compensated power detection. There's a 2-stage receive LNA here. And there's a reference in the paper where you can see a lot more detail on that. This is something we at PRFI designed for one of our clients. They gave us a specification. We went away and did the design, and we looked after the packaging. And this is in a 5mm by 5mm QFN package. and that has a custom lead frame inside, which we designed, and we also designed the PCB. Now, if you look at that, it doesn't look very different to a 2 gigahertz or 3 gigahertz part you might buy off the shelf, but it does take a lot more effort to put an IC operating at these frequencies into that package and for it to work sensibly. And you can see here, we've got some low frequency decoupling capacitors here, but we just go straight in and out with the RF lines there. This is another little example just to show you those who aren't familiar with this style of package. This is another overmolded plastic package. It's a 4mm by 4mm 20 lead QFN. You can see here the exposed panel on the other side, and that will normally be soldered down. You see this IC looks quite small. In actual fact, it is pretty much the maximum length you can get inside of this. I'm going to show some images now of the inside lead frame of that. On the inside of the package, you have a die attach area onto which you mount this IC. So this shows a lead frame. So what you have a big panel of lead frames, and they come looking like this left-hand image here. And this is a standard open tool lead frame. And the red area here is round about where the edge of the plastic body is. And so then at the end of the packaging, you cut around this and you're left with that QFN part you saw in the previous image. You can see these corner ties here. These are to keep the die attach area in place. Now the blue square here is where we might put a microwave or a mmWave IC. And what we do is we try and adjust the chip size so it gets close to the edge here to minimise the bond wire inductance. More on this later. Something I'll come back to again, and I'll say it several times because it's very important. Don't design an IC and then look around for a package. You need to design the IC with the package at the same time. It's a concurrent engineering process. So, what sort of packaging effects do we get? Well, if you put an IC, mmWave IC into a package, you get parasitic effects that degrade performance. First, dielectric loading, both loss and permittivity of the plastic in contact with the IC. Secondly, you get grounding inductance in the package itself, but also in the PCB. Now, it's all well and good putting an IC into a package, but if you then can't put it onto a PCB, you're not going to have very many happy customers. Series inductance of the RF bonds. This is probably the most obvious parasitic effect that everybody thinks about. And there is stuff we can do about it, and we'll come on to that. And increased thermal resistance. And this obviously leads to increased junction temperature, which leads to reduced lifetime. So the first issue we can mitigate by passivation. And many IC processes include passivation. A lot of gas processes include PBO or BCB passivation. Many GaN processes offer passivation as well. Now, this passivation will to some extent degrade the transistor performance a little bit, but not half as much as putting overmolded plastic on top of it. And the PDKs, the process design kits, normally include models with the passivation in place. And if you use a process with passivation, the effects of the plastic on the RF performance tend to be quite modest. You can, of course, still EM simulate them, and we do. So we have a stack up which includes the IC itself plus some plastic molded compound on top of it. Another option you've got is to use a cavity package. We'll come up with an example of that, show how that works. The second issue, grounding inductance. this can be a very serious problem. This can cause misery for people. And people can buy an IC in perfectly good faith and then select the long PCB substrate, end up with too much grounding inductance and have an oscillator rather than an amplifier. It's very important to minimize grounding inductance. So with the IC, you've got the availability of through substrate vias, these are very helpful in reducing the inductance from the IC to the die attach panel. But, as I mentioned, you've got to take a lot of care when mounting the packaged IC onto the PCB. And this tends to dominate the grounding inductance of SMT package components. You can't compensate for this. Once you put that grounding inductance in place, that's it, it's there forever. What you have to do is minimize it and make sure the grounding inductance you have is tolerable. Things get worse as gain increases and as frequency increases. Third issue, bond wire inductance. It requires careful consideration, particularly above 20 gigahertz. But there is something we can do, and we'll talk about this. And you can compensate for this quite nicely. The capacitance of the PCB pads and the RF pads on the IC actually help with this. So, common lead inductance, vital that this is minimized. You can't compensate for it. So how much can we tolerate? Well, we did a little analysis to work this out, and the approach we took was to take an ideal amplifier, and it was just a waste to block, in honesty. We had 100 dB return losses and 200 dB isolation. It's a great amplifier. You know where you can buy one, let me know. And we said, well, let's put in grounding inductance until the return loss degrades to 20 dB. So quite modest, it's still a perfectly decent match. So you know, the inductance we're coming up with here is perfectly tolerable. You can probably tolerate a bit more than this, but if you can keep the inductance down to this level, you'll be laughing. We looked at amplifiers with 10 dB, 20 dB, and 30 dB of gain. And then we worked out the maximum inductance that would degrade that return loss to 20 dB. And this is what we saw. 10 dB, 20 dB, 30 dB. This is the maximum inductance. Maximum in inverted commas. You can probably tolerate a bit more, but if you keep it down to this, you'll be laughing. And what you see is two things. Firstly, as your gain goes up, life gets a little bit harder. It's pretty easy to put an attenuator into an SMT package and not worry too much about the grounding inductance. Although, actually, that said, if you're trying to get a high level of attenuation, you will start to see that isolation impair on that attenuation. When you're up at 30 dB here, even at 10 gigahertz, you can only tolerate 5 gigahenries of inductance. That's not a lot. This is why it's not sensible to put loads of gain into an SMT package component. This is why, if you look through the catalogues of sensible companies offering SMT package microwave ICs, you can only get gain up to about 25 dB or so at microwave and millimeter wave frequencies. Because if you've got more, you can never get the grounding inductance low enough for it to behave sensibly on a PCB. This is 20 dB here. And you see, we're saying at 40 gigahertz, we need about 4 picohenries. This 4 to 5 picohenries, it's about the lowest practical inductance you'll get from a sensible thin substrate. You might push it a little bit lower. You can use grounded coplanar waveguide, that helps a little bit. But don't put 30 dB of gain in an IC you're then going to put in an SMT package. You'll be sorry. This is a PCB. And this is a nice example. I know that because we designed it. This is for a standard product offered by CML Microcircuits. It's a 26.5 to 29.5 gigahertz PA. 21 dB again, relatively modest power, 25 dBm. Now the things to point out, can you see here, the die-attached panel, absolutely full of wires. Now we actually use copper-filled wires because that helps thermally as well. We've also got additional wires extended that ground panel here. Just pull down the inductance, and unused pads are grounded. And think of it as like the ground sheet of a tent. If you're not using it, put a stake in it, connect to the ground. Life will just be happier. If it's not being used, ground it. We've got here, it's a loosely coupled grounded coplanar waveguide. So this is ground here. You see the grounds are relatively close to the RF track here. And so we have grounded coplanar waveguide in and out. This ends up with a really nice low inductance ground. These are just some SMT components here. So we're going to talk about bond wire inductance now. When you first start looking at bond wire inductance of an IC, and you look at the inductance, it's terrifying. You think, how can I ever cope with any inductance at all? The first step is to minimize that inductance. So you use 2 or 3 bond wires in parallel. Then you lay out the die to fit the package. You work with the package manufacturer and the assembly house so that you select the die to minimize the bond wire length. And you can use techniques such as reverse bonding. That's where you start on the package and go to the IC. That can reduce your bond wire length a little. Beyond that, we can compensate for the series inductance, and I'll explain a little bit more about this with some nice example simulations. What you do is you use the capacitance that's there anyway on the PCB pad, and the capacitance that's there anyway on the IC bond pad, and you optimize these to generate a low-pass filter. Then you've got C, L, C, and that's better than just L. Then you can simulate the transition and attempt to optimize it. This is a bond wire. These are three bond wires. And you see here, we spread them a little at this end to reduce the mutual inductance. And then we simulated this in ABS using, they've got quite a nice bond wire model. Other simulation tools are available. What we discovered at 28 gigahertz, these 3 bond wires, they're just 0.75 millimeters, which is very tiny, too tiny for me to see these days. That comes to 0.21 nanohenries. That sounds a really low inductance. Here it is on a Smith chart. So we just grounded one end, plotted it on a Smith chart, and comes to 0.21 nanohenries. Now if you look at this as a 2-port, 0.21 nanohenries, that's great, but actual fact, the S11 hit 15 dB at about 12 gigahertz, and it hits 10 dB at about 22 gigahertz. So you're looking at 40 gigahertz, you're at 7 dB, that's awful. What are you going to do? You can't reduce the inductance anymore. Fortunately, the world of filters helps us. So all we've done here is put a capacitor each end of that wire, and we formed a low-pass filter. And you can see now we pull this down, we've got a lovely match, 20 dB to 40 gigahertz. Hardly any loss because it's a perfect filter. We've not included any loss in it. But you can see here the approach you can adopt to compensate that series bond wire inductance. This graph shows you the most inductance you can tolerate in a perfectly compensated filter. Now this isn't the limit, you can live with a little bit more, but if you want perfect compensation for a perfect 50 ohm match third order filter, this is the maximum. And you see, if you get down to, we were up about 0.21, you see here, just over 40 gigahertz. So you need to get down to about this 0.2 nanohenry level to get up to 45 gigahertz. So custom lead frames, I mentioned these earlier. These are 2 examples. This is one of an IC we did, 28 gigahertz PA. So first of all, you can see the 3 bond wires here. See how the IC goes all the way to the edge of the die attach paddle? Now, we take it as far as the assembly rules allow. Do check with the assembly house before you manufacture the IC, as people get awfully upset if they have to pay for your ICs to be remade. And you can also see what we've done here is we've fused some of these pins to the ground paddle. This helps reduce the inductance, it helps it thermally. You also end up with a ground single ground style transition here, and it works really nicely. We've got the same on the output here. See, we've got a couple of other unused pins here that we had, and we grounded these. And this happens to be between the gate contact and the drain contact here. This is another example. There's a reference for this in the paper. This isn't one we designed, but you can see they've used the same approach. They've grounded some of the leads to the die attach paddle. You can see also they've increased the size of this landing pad here, and they're trying to optimize the capacitance of this transition. They've also done away with these corner ties, and they can do this because they've got fused paddles, fused leads each side, so that will support the lead frame. Now the advantage to this is you don't run the risk. You can imagine here the hypotenuse is the largest thing, so you can imagine if you're not careful with your PCB design, then you can end up with something that's physically large, and you can end up with some suckouts. Now we designed the PCB carefully as we did here, and with this lead frame, we never had any issues. But they've taken a different approach to avoiding this. The thermal effects, this is just a single slide. You know, this could be a whole presentation in its right. So the higher the junction temperature of a transistor, the lower the medium voltage. And the maximum junction temperature you can tolerate depends on the process. So the thermal resistance of the package, the PCB, and the assembly, the die attach of that IC to the package itself, they all add to the junction to base thermal resistance. Now, with a QFN style package, it has a solid copper base. Actually, it's a copper alloy. It's very good thermally. Custom lead frames, as I mentioned, they can help further with the thermal impedance. The thermal resistance of the die attach material, this is important. Now, when you go to an assembly house, they'll have a default epoxy that they like to use, and normally it's got pretty lousy thermal conductivity. And the reason for that is because it has other things that make life easy. It has a Young's modulus, that means it's quite compliant. So it's easy to attach a range of dies without trouble. The thermal performance of the IC is also critically dependent on the board material. Now the IC manufacturer, they'll ignore that. They will tell you what the junction to case thermal impedance is. And that's great, but you're then responsible for keeping that case at that temperature. But when you put that in a product that's on a PCB, the person who's using that product, they're not really interested in the case, they're interested in the temperature of their product. So you need to consider that. And I mentioned we use copper filled vias. We use a thin substrate because that helps with the grounding inductance low. We use copper filled vias because that helps thermally. This is an example of an air cavity package. And what you can see is it looks very similar to an SMT package. And this is just a plastic lid stuck on top. Generally the die attach paddle is a bit smaller in an air cavity package because the walls need to be self-supporting. But to look at it doesn't look much different unless you try and put a soldering iron in the top of it, which I've seen done, and you can tell it's an air cavity package. That was the IC that popped in there, 39 gigahertz gas PA. This is another one we did. This is a 28 gigahertz Doherty PA. And there's some information on this in our website, and there's a reference paper on our website as well. This is a commercially available air cavity package, and you can see it's got the same ground signal ground. The input and output were at the centre. Here we've used a Lange coupler at the input to get the quadrature split for the 28 gigahertz stability. So it's not perfectly lined up. So this, you know, it's not an ideal package, but we didn't want to pay for an ideal package, so we took the best we could get, and it works pretty well in this package. So laminate packages I'm going to discuss now, and you can buy commercially available laminate packages. This is one we designed and we had manufactured via Filtronic up in Newton Aycliffe, and they have a means of manufacturing this style of package, so we designed it, we got them to manufacture it. This has got two 26 gigahertz gas PAs. Again, there's a reference in the paper, you can find out loads more information on this if you're interested. And you can see there's three inputs here. These wires here go through to the underside, to an SMT pad on the underside here. You've got a little laminate lid that goes on the top here. This strangely shaped transition is all about keeping a good 50 ohm transition from the bond pad to the PCB. So it looks pretty straightforward, but it does require quite a bit of careful design to get right. This is a more involved package. It's exactly the same packaging technology, but what we've done here is we've included some filters in the base of the package. So this is a way of really getting some added value in without any significant added size. So this is an FM, so these are commercial available parts, a PA, switch, and an LNA. You see there's a harmonic filter here at the output of the PA. You see this is a couple line receive filter. We'll just bend this like that to shrink up the size a little bit. All VM simulated. Assembled onto a PCB, we designed it for a PCB, some expensive RF connectors on here, and we made that, measured it, and again there's a paper referenced in the paper from this conference, and you can download all the papers that we wrote, you can download from our website free of charge, just go to the papers page. And yeah, that worked nicely, we're very pleased with that. Multi-chip modules, I'm not going to go into huge detail, but you can put dye onto the surface of a PCB, and this is an example of that. And you can use this approach. You can get up to 100 gigahertz and beyond. This particular example was about 43 gigahertz. You can use bond-to-bond dye. This is an example of an air cavity package. It's a fantastic piece of engineering. I believe it was funded by the US DoD, a paper here. But you can imagine this is quite an involved thing. This is a 16 element transceiver, and then you put a bunch of these into an IC. You've got little patches here, and there's an aperture coupling into each of these packages. And then there's a spacing of lambda 2 at 94 gigahertz. Then lambda over quarter at the edge, so you can tile multiple onto these. Great bit of engineering. I don't know if it's used in practice. And wafer level chip scale packaging. This is used by people like Infineon and have a wafer level chip scale packaging process that's used in commercially available ICs. This was an example from Sumitomo. So they add some extra layers. It was a gas PM process. They had extra layers to do what they call redistribution. This is a ground layer they have, and then they route out to a sort of ball grid array type thing beneath. What you'll notice here, this is their evaluation PCB. They had a bunch of different ICs. You'll notice here, ground signal ground, and they evaluate it using ground signal ground probing. So they get away from that problem of having the ground inductance of a PCB. But ultimately, you have to think, well, how am I going to use this in practice? Will I then incur that grounded inductance? So, just to summarise then, plastic overmolded SMT packaging, very popular. currently used up to around 40 gigahertz, not a hard limit. Air cavity packages avoid the effects of the plastic overmolding and can push the operating frequency higher. Very good RF grounding is essential, particularly with high gain and high frequency, and it's strongly impacted by the design of the PCB. The RF port series inductance, you need to reduce it to an acceptable level, and then you can compensate for it by using capacitances that you're going to get in there anyway. You need to model that RF transition and optimize it, but you can do this quite effectively to millimeter wave frequencies. We touched on wafer level chip scale packaging. That really can have a true chip scale size package and helps reduce the packaging parasitics. Antenna in packaging technology. There's some impressive examples out there that offer you a very compact solution at high millimeter wave frequencies, but it is very application specific. That is all I was planning to say. Happy to try and answer a question or two we have.